Hello, this is day 4 from Unit 5 or Chapter 11A in the book, and this is about radicals. We've touched on this a little bit, mainly as it relates to the fact that fraction exponents can be rewritten in terms of a radical. So here are some examples. This is a radical, the radical sign. It means this one in particular means a square root because it doesn't have an index. And when it doesn't have an index, it's the most basic one. It's a square root. So it's an index of 2. And that's important to know because if we're going to simplify this, it may be helpful to write this as fraction exponents just to kind of see. There's a couple of different ways to do this, to think about this. Maybe I want to split it up into square root of 64 and square root of x to the 12th. Reason being, because square root of 64 is easy enough. We know square root of 64 is just 8. What number times itself is 64? So that would turn into an 8. The square root of x to the 12th, that may be a little more challenging. We can think of this as in the same way that it could be 64 could be thought of as 8 squared. And since this is a square root, the index is 2. The index and the square would cancel each other out, and you'd just get 8. That's one way to think about it. In the same sense, you would want to pair up, or really split the x to the 12th into as many pairs of 2 as you could. So that would look like, square root of x squared, square root of x squared, all just multiplied together. And you have to do this a number of times until you have all 12 x's accounted for. Oops, all 12 x's accounted for. 2, 4, 6, 8, 10, 12. And so you'd see that, the square root and the square would cancel each other out for each of these. And ultimately you'd end up with just x times x times x times x times x times x, which is x to the 6th. But there's an easier way. If I knew that I can write these as a fraction exponent, this would be really x to the 12 over 2. Recall that the exponent becomes a numerator, and the index of the radical becomes the denominator of a fraction exponent. So the reason I'd like to do this is because 12 divided by 2, I can simplify that fraction. It would just be 6. X to the 6th. So it's helpful to turn the numbers underneath the radical into what number they would be with an exponent. And specifically, you want it to be a number with an exponent that's divisible by the index, okay, because that becomes the denominator. So it's okay if that's confusing. We'll write this. We'll keep going. This first one said, simplify the expression. This next one says just express with rational exponents. So we don't need to get super crazy. It just wants us to express with rational exponents. And, we could simplify where we can. So if we split this up, this is, 4th root of 16 times the 4th root of s to the 12th times the 4th root of t to the 15th. And then kind of simplify what we can. The 4th root of 16 can actually be simplified. Okay, so here's the power. So we're looking for, the 4th root is saying some number to the 4th power is 16. So here are all the numbers, 2, 3, 4, 5, 10 raised to the 4th power, and 16 is right here. So we see that 2 raised to the 4th is 16, and that means that the 4th root of 16 is 2. So I want to express it with rational exponents, and I could have, the 16 could have been 16 to the 1/4 power, but I could simplify it as well, and now it's even better. The s I could write as rational exponents. This would be s to the 12/4 power, but then that can be simplified to 3. S to the 3rd. T would look like t to the 15/4, And that can't be reduced, so we'll just leave it like that. That is a rational exponent. That's what they wanted us to simplify it to, or to write it as, rather. And so in this question, we simplified things, and anything we couldn't simplify, we left as a rational exponent. This problem could be interpreted, just so we're clear, as it could be interpreted as just expressed with rational exponents. And if that was the case, it would just be 16 to the 1/4, s to the 12 fourths, and t to the 15 fourths. And then we would go about, some of these we should simplify, like s to the 3rd or whatever. And if they're not asking to simplify, we could leave 16 like this. But I interpret this as we're simplifying it, and then anything we can't express as rational exponents. And then we could go backwards. We want to take this term here and express it as one radical, meaning we want to have some radical with some index right there, and then everything underneath there. In order to do that, we really need all of the, if we have just one index, one type of a radical, that means we have to have all of the denominators of the exponents to be the same. So right now, 5 doesn't have an exponent. We can think of it as a 1 or as a fraction, 1/1. Okay, so 5 is just to the first power because there's no exponent. And then, 1 I can write as a fraction, 1/1. X has to the 3/4, okay, that's okay. Y is to the 1/2, all right? So they have fraction exponents already. That's good. However, if we're going to write it as one radical, we need to all have the same denominator. This is basically just making a common denominator out of each of the fractions, which we should have some skills in. It looks like, I can't reduce 3/4, so 4 is going to be the least common denominator. So that tells me my radical is going to be a 4. And I can change 1/2 to have a denominator of 4. I would just say that 1/2 is the same as 2/4. Or, to get the denominator to be a 4, what does 2 need to be multiplied by? A 2. And then multiply the top by a 2 as well, you get 2/4. And same thing with 5. 1/1, I need it to be 4 on the denominator, so I times it by 4/4. This is just making common denominators. And we had the skill from adding fractions. And no, we aren't adding fractions, but we do need to make a common denominator so that we can write it all under one radical, because the denominator is the index of the radical. So 5 becomes 5 to the 4/4 power. And now we see that everything has a denominator of 4. So we would say this is 5 to the 4th. Okay, the numerator stayed with the number, and the denominator became the index of this radical. X, numerator of 3, so it's x to the 3rd, and then y, numerator of 2, so x squared. Again, the denominators were the index of the radical. This is written as one radical. The 4th root of 5 to the 4th, x to the 3rd, y squared. Similarly, we could express this all as rational exponents. This is just going backwards again. So we could just kind of see what we got. Remember, the exponent is the numerator. The index of the radical is the denominator for each of these. So r to the 7/3, s to the 5/3, t to the 24/3. And there's nothing to simplify for r in terms of its fraction, just like to reduce it. Same with s. T I can reduce it be to the 8th power, because 24 divided by 3 is 8. So r to the 7/3, s to the 5/3, and t to the 8th. Okay, so they all have rational exponents. This 8 is a rational number. Any whole number is a rational number because I could make it into a fraction, a ratio rational, by putting a 1 under it. So that me reducing it is just common practice. Oh, yeah. So this is fun. We can solve problems, solve an equation for x, or a variable, that has a fraction exponent. And it's not overly difficult. However, we do have a little prep work. We need to get x by itself. So this is basic solving to begin. We want to get 9 out of there first. So we have the opposite. We have 1250 equals 2x to the 4/5. Okay, next would be divide by 2. All right, we get x to the 4/5. And this would be 625. I'll show you the way that can kind of take this down rather quickly. I want to get x by itself. I'm going to raise it to the reciprocal power, 5/4. The reason why is because now I would notice that x has a power, and then this whole term has a power. So I have power to a power property, and I chose 5/4 because power to a power property is multiplying your exponents. And I chose 5/4 because that would, if I multiply the exponents together, I would get 1, thus eliminating my exponent. However, I have to do the same thing to the other side. So this becomes x. We did it, it's by itself. But we need to know what 625 to the 5/4 is. So I would write this as a radical, 4th root of 625. And recall from a prior video, the numerator that becomes an exponent, I could put under here 5 with the 625, but I'm going to choose to put it on the outside. This is also one of the options because I want to get 625 to a more manageable number to even see when it is. And a root makes numbers smaller. An exponent makes numbers bigger. So I don't want to take 625, raise it to the 5th power, get a huge number, and then try and take the 4th root of it, because I'm trying not to use a calculator here. So I'll take the root first. So the root, 4th root of 625 is 5. And then I have to the 5th power still. So 4th root 625, you could scroll up and check this out. We're looking for the 4th root. Anything that's raised to the 4th power that is 625. It's right there. The answer is 5. So 5 to the 4th is 625. The 4th root of 625 is 5. And then to the 5th power, we have to raise 5, and we would get 3125. Also on that list. All right. So really the main new thing here that we've kind of seen before is that if I want to get rid of an exponent, I can raise that term to the reciprocal power. And then power to a power property applies. We'd multiply them, we'd get 1. And x to the 1 is just x. And then your assignment can be rather long, I think. There's a couple problems on here. So if you get the gist of some of this, as we've talked about before, it's okay to skip some, but you want to make sure that if you look at one and you're not sure if you know how to do it, you should attempt that one, because that's where you'll grow. If you look at it and you're positive you know how to do it, sure, it could be good for practice, definitely. But that would be a candidate to skip if you are doing so. Just don't skip the ones that look hard, because that's where you can expand your mind. All right, I'm going to choose one random problem and do it. Oh, boy. I like number 42 because I imagine people don't like number 42. When I look at this, I'm going to see right away, I want to notice right away that, yeah, I got this one half hanging out here. But on the inside, I notice that a number to a power and a number to a power, or b to a power and b to a power, I just said b twice. They both have the same base. If they do, I could apply that one rule where I can subtract my exponents. So that would look like b to the 2n minus the next exponent is a negative 2n. Okay, so I just combine these things with their exponents subtracting, and I still have the stuff to the 1/2, and I'll worry about that later. But 2n minus a negative 2n is really plus a 2n. 2n plus 2n, which is like terms, you would get 4n. b to the 4n power. There's another way to do this. I'll just take a brief pause and not really do it, but b to the negative 2n has a negative exponent. This thing could have been brought to the top and been a positive 2n. b to the 2n times b to the 2n, you would add your exponents and get 4n. Anyway, the next thing would be, I should write this maybe, I have power to a power here, so that might be fun. Power to a power would be 4n times 1/2. And if you need to take that off to the side to do it, 4n times 1/2, that's fine. 4 over 1, multiply this stuff out. We have cancellation terms here. 4 and 2 are going to cancel with the 2, but whatever. You'd get 4n over 2 if you multiply these fractions, which is 2 and 4 are reducing to 2n. So if I multiply these things together, power to a power, I get b to the 2n. Neato. I chose to do that problem because it's a little messy. Sometimes people struggle visualizing what that looks like. But good luck, and be sure to look at previous videos if you're not remembering some of these properties. All right, thanks.